All right, welcome to the DAFoam 2022 workshop. And my name is Ping, and my co-host is Bernardo. Bernardo, do you want to say hello?
Hello, nice to be here.
All right, thank you, Bernardo. This is our second DAFoam workshop. We have about 30 people sign up, and now I see about 20 plus people showing up. That's very good. And I hope you have a great summit so far. All right, so today, our workshop has 3 objectives. First, after this workshop, you should be able to get familiar with the new features and interface in the new version, DAFoam version 3. I'm going to talk about the features later. And second objective is that you should be able to run aerodynamic and aerostructure optimizations because we have some hands-on examples for you to run. The last objective is that you should be able to learn how to modify or add DAFoam's C++ and Python codes to if you want to have a new feature. These are the 3 objectives for this workshop. A few notes like last time. Here are the few notes. We assume that you are familiar with DAFoam version 2. Which means that in this workshop, we are not going to go into the details of, for example, how to add a volume constraint and such. Instead, we focus more on how to use the new interface in version 3. And this workshop also have some hands-on examples. And if you install Docker, you can follow the instructions to run an aerodynamic and aerostructure optimization. And this workshop is supposed to be interactive, which means that please stop us at any time if you have any questions. But if you don't have any questions, please mute yourself. We will record this, as you can see that I'm recording this. After that, I'm going to upload the recording to YouTube. And all the material, including the slides, is available at this address. It's an open source repository. If you go to workshops 2022 summer slides, there will be a PDF for the slides. All right. Here is the outline of this workshop. We have 5 sections, 5 topics, and introductions, OpenMDAO tutorial, aerodynamic and aerostructure optimization, and how to add new features. We will probably have 3 sections. Each section will have 45 minutes-ish, and then after that, we will have a 5-minute break. Okay. Let's go to next. Okay, version 3 introduction. Yeah. First, what's DAFoam? It's short for discrete adjoint with open form. DAFoam develops an efficient adjoint methods for high fidelity MDO. It has 3 main features. First, that is based on the open source package OpenForm for multi-physics analysis. And DAFoam itself implements the discrete adjoint methods. Just keep in mind that DAFoam does not use the OpenForm's built-in continuous adjoints. It has its own discrete adjoints. The third main feature is that it has this is a new feature for version 3. It develops a Python interface that allows DAFoam to talk with OpenMDAO for large-scale MDO problems. And then I go to next. What's new in version 3? As I mentioned, version 3 actually is a major release that integrate DAFoam with OpenMDAO. The main Python interface is this emphasis_DAFoam, and that allows DAFoam to talk to OpenMDAO through this emphasis, this new package. We're going to talk about emphasis later. And another note is that most of the settings are same as version 2, which means that if you have a version 2 script, you should probably be able to run it with version 3. It's compatible. So DAFoam version 3 is compatible with all version 2 run scripts. But if you want to use version 3, you have to update your dependency versions. Check the DAFoam website. We have a new installation guideline. Next. All right. Before I talk about how to use the DAFoam version 3, it's better to first look at an OpenMDAO tutorial, because from the survey, it seems that not everybody used OpenMDAO before, but DAFoam version 3's run script, essentially it's an OpenMDAO run script. So which means that we have to first learn how OpenMDAO works. This is just a very, very simple tutorials if you are interested in more advanced usage for OpenMDAO, check their documentation website from here. Obviously today we won't be able to cover that. So I'm going to start with a very simple example. Here it is. This is two component systems, and this red box is a so-called implicit component. This green box is an explicit component. So this is the governing equations for the implicit component. This is the expression for the explicit component. And this red component receive variable x as the inputs and solve this equation and output variable y. And they will give this variable y to the objective component, which is essentially an explicit component, meaning that you can directly compute output f based on the input y. But for this implicit equation component, you can't do that. You have to use, for example, a Newton solver to solve for y iteratively. That's why it is called an implicit component. So the optimization problem is that x is our design variables. We are trying to figure out what's the best x that minimize the output function f. So, okay, this is a very simple optimization problem. But the question is that how do we use OpenMDAO to solve it? Now let's look at the next slide. Okay, now let's do some interactive exercise. So what I'm going to do is that I don't want to show this right now. I have a terminal, and there are two ways to run these problems. If you already have OpenMDAO, then it's easy. You just go to the folder, which is, let me show you. The very first thing is to download this workshop from this address, from the repository I just showed you, which is, let me show you. From this repository, github.com, DAFoam Workshops, okay? And I already download it, and I put it on my in my desktop directory. Okay, once you download this, you can go to this workshop directory, and you can go to 2022 summer and examples.
Dang, sorry to interrupt, but I'm not sure if I'm the only one, but I can't see your terminal.
Okay, maybe I somehow didn't share that. Thank you, Bernardo. Can you see my terminal now?
Yes, that's better. Thanks.
Thank you. So let me clear it. So as I mentioned, I already downloaded this to my desktop. And this is in my desktop directory. So if you go to Workshops 2022 examples, there will be a subfolder called OpenMDAO. You just go to OpenMDAO. Okay. So if you already have OpenMDAO installed on your computer, you can just run Python, run script, issue run. But assume that you don't have it. I want you to use another way to run OpenMDAO, which is through this DAFoam Docker image. Hopefully you have installed Docker, but if you have not installed Docker, here is, let me see if I copy the link. And I guess you can see my web browser here. There are some instructions in terms of how to download this image, how to install Docker. Because we're going to use Docker to run the aerodynamic share optimization later, so that's why it's better to just get it installed right now. So we have instruction for Ubuntu if you use Linux, Mac OS, and Windows 10. Okay, so once you install Docker, make sure that you verify it. Actually, I have not opened my Docker app yet. You can type Docker version. You should be able to see your version. And then you can run this command to download the DAFoam package version 3.0. And this package, this image is about 1.5 gigabytes. It may take a while. So let me see if we can download it. if you have already downloaded it, you don't need to download it again. Let me see if I run this command. For example, if I copy paste this command, you will say, oh, it's already downloaded. Okay. Then what's next is that download this workshop example. I already downloaded it. And then let's go to the next. Okay. The next step is to use the cd command to go to this directory, OpenMDL, which I'm already in this directory. And then what's next is that assuming that you already have the DAFoam Docker installed, you already download this DAFoam package. And what's next is that you copy this command and paste it here. And I guess some of you are still downloading the Docker image. So let me explain how this process works. We have a what we call Docker image, which is a pre-built image that has all the DAFoam dependency, DAFoam code, and Mark Arrow modules compiled. It also has OpenMDL, which means that when you run this command, assuming that you already download the image, you will create a so-called container. And this container, you can think of it just a virtual system. So when you are in a virtual system, you should be able to see something like this. The first DAFoam user is the username for that container at this address. It's a bunch of random numbers, which represents the randomly generates machine name. And then you should be in this mount directory. This mount directory is in the container. You will be linked to your directory when you run this command. So when I run this command, I am in this folder, right? So which means that right now, this mount folder will be linked to this folder on my computer. So if you type ls, you should still see this run script.py. So then what's next is to just run Python. And that's it. So when you run Python space run script.py, you should be able to see that where OpenMDL managed to solve this problem, and the optimal design variables around 5.5, and the optimal objective function is 0.875. Okay, it ran for 11 iterations. It called function evaluation 11 times, gradient evaluation 11 times. Okay, so let me know if you have any questions or problems, and I want you to run this case, because once you have the Docker, it should be very straightforward to run this case. All right, let's move on to the next page. Assuming that you have managed to run it, and well, by the way, this slide just show you an alternative way to run without a Docker. So if you don't want to use Docker, you can just pip install OpenMDL and then go to this folder and run it. Okay, so it should be the same. But the reason again we use Docker is that we can use that for aerodynamic optimization later. I guess I can move on to the next page, which is the N2 diagram. So after you run the case, if you type ls, you should see that is a new file that is generated called n2.html. This is a diagram which is very important when you use OpenMDL. You can illustrate the interactions. It can illustrate how many components are in the system. It can also illustrate how do these components transfer data. So let's open this N2 diagram. Okay, so I'm going to open it from my computer here. And then I should be able to share that to you. Now you should be able to see this is an N2 diagram already shown on the left, but the font size is a little bit small. And this is a very interactive interface. You can increase the font size if you cannot see it well. But let me remove the equations. Okay. So this is the N2 diagram. If you remember, we have two components. One is called implicit equations. Let me put this side by side. And this is our problem, okay? And this is the corresponding N2 diagram from OpenMDL, which is defined in the run script.py, which we will talk about that later. But let's first look at N2 diagram. And we have two components, implicit equation and objectives. And this light blue or cyan color denotes a component. We have the implicit equations, objectives, and then this implicit equation component has x as the input right here, and compute y as the output, which corresponds to this diagram on the right. If you look at the N2 diagram, we also have our objective component, which uses y as the input and output f. So we're going to set this out in the wrong script. And then how do they transfer data? So if you look at this right-hand side diagram, the implicit equation component will pass y, which is output, to the objective component as the input. So which means that this y is the only data transfer between these two components. How can we visualize it in this N2 diagram, which is right here? You can see that if you click this, if you left click this, it will show you the data transfer. So the x variable is the input. It will compute y output. And if you see a gray box here, which means that there are some data transfer between these two components, the y of the implicit equation will be passed to the objective component and use it as the input. So which means that this N2 diagram fully represents what we want to optimize. So this is very important when you have neuron scripts to verify that if the system, especially the components and the interaction, and matched what you want to optimize. All right, this is the N2 diagram. I'm going to go back to here. Let me go back to this. The next is that let's look at the run script. How do we set this problem up using OpenMDAO? The only thing you need to do is to create this run script of pi and set up some thing over there. So let me show you. Okay, so this is OpenMDAO run scripts. You can see that it defined a class called implicit equation. It also defined a class called objectives. And then you use these two classes to do optimization. Let me first explain what's this first class. Of course, you need to import OpenMDAO as OM, okay? So this implicit equation, this class basically define this, okay? So you need to create this class, which you inherit from this implicit component, because this is an implicit component. You cannot directly compute y based on x. That inside this class, you need to define a few functions that set out the input and output and implement how to compute output based on the input. Okay, so for example, in this class, you need to have a setup function that define what's the input for this component and what's the output. Obviously, in this case, the x is the input and y is the output. Okay, so it's very straightforward. And the second function basically define how do you compute the partial derivatives. Ideally, we want to compute this partial derivative, which means that partial y, partial residual, partial x, partial residual, partial y, using some analytical methods. You can hand derive the derivatives, or you can use automatic differentiation. But because that this is a very simple problem, I just say that use finite difference to compute the partial derivatives, then OpenMDAO will compute that automatically for you. But you can imagine that if you have many input and many output, this method is not very efficient. But because this problem here only has one input and one output, we can just use finite difference. And then the last function we need to define is for implicit component, we need to define a function to compute a residual based on the input and output. If you look at this apply nonlinear function, and it has inputs, outputs, and residuals. So because you already define what's input, then you can use the inputs x key as the x and the outputs y key as the y. Then you get a value for the input and for the output. And then you can compute the residual, that's the expression for the residual. By the way, you need to compute residual for each output, because this problem you only have one output and you only have one residual. But if you have multiple outputs, you have to compute residual for each output. So this is the expression essentially this. We define this guy as the residual. We want to drive the residual to 0 when we solve this component. That's why we define it here. So exponential function minus y. Okay. And you might notice that we have a 0 index here because OpenMDL assumes that all input and output are vectors, which means that they're arrays. So if you only happens to have only one value for the inputs, you just use index 0 to refer to get the value. So these are the 3 minimum functions you need to have to define an implicit component. Very similarly, I go to the next. Very, very similarly, you do the same thing for the explicit component here. But the only difference between the implicit and the explicit is that for the explicit component, you need to define a function to compute output based on the inputs. Because it's explicit, it should be very, very straightforward to compute output based on the input. So, but for the implicit component, you can't do that. So that's why OpenMDL will ask you to define the residuals. Then OpenMDL will solve this component for you. All right. After these two components are defined, we will create an OpenMDL problem and add these two components to the OpenMDL problem. We use this add subsystem command to add implicit components and give the class we defined above. And then we add a subsystem objective components and use this objective class. So you will see that later that the DAFoam's run script will look very, very similar to this. And then once we add these two components, and well, we need to set up a connection as well, but because the output of this component, the name is y, which is the same name as the input of the objective component, then we can just promote all of the input and output, and then will automatically connect this input and output for you. This is just a very simple example. We use promotes, but obviously today we don't have time to explain how this works exactly. I suggest you refer to this link to look at the details how this promote works. It's just a way to facilitate the data transfer setting. Otherwise, you have to manually connect every component's output to another component's input. So once you add a subsystem, we add components, promotes input and output, set data connections. And because we have an implicit component, we also need to set out the solver to solve for it. In this case, we use a Newton solver to solve this implicit component. And after that, we can set out the design variables. We say that X is our design variables and F is our objective function. Okay. You can set out anything you want as an objective function. You can, for example, I don't want to optimize F. How about I just want to minimize Y, and then you can just add objective function Y. Okay, it's very, very flexible. And after that, we set out optimizer parameters, which is very, very similar to the version 2. In this case, we just use SQP. And then you call this set out problems, you call run driver, basically it's run optimization. And then after that, you print output, print the optimal solution. Okay. Now, this is just a very simple example. I'm going to show you another thing that is very flexible in OpenMDL, which is that, for example, what if I want to add a constraint? How do I do that? So you just copy paste this line. Instead of saying add objective, you can say add constraints. So you can set any variable as a constraints. For example, what if I want to set a y as a constraint? So during an operation, I say y has to be greater than 0. So lower is 1.0. You can just set out something like that. Okay, so then the problem is slightly reformulated such that the variable is x, objective function is still y, but we have a new constraint that is this y has to be greater than 0. Okay, so if you run it, let me see if it runs. So it still runs, and again, the optimal solution obviously is different from the previous one because that you add a new constraint. So make sure that when you add a constraint, that this constraint is a reasonable constraint. So any questions for this problem? Okay, if no questions, let me quickly summarize this tutorial, which is here. So basically, in summary, to use OpenMDL for optimization, we need to write classes for each component in the system. We need to define the inputs and outputs. We need to implement the way to compute the output if this component is explicit, or if this component is implicit, we need to implement a way to compute the residuals. And then one need to add this component to the optimization problem in the run script, in this run script right here. Okay. And then when you add them, after you add them, you need to set up the connections. How do they transfer data? And then you need to set out the design variables, set out the objective function and constraint functions, and then run the optimization. So a new open source interface, which is based on OpenMDAO, this interface is called NFIS, was recently developed to rewrite the mark arrows module, for example, PyGeo, IDWAP, into the OpenMDAO component formats. You can see in the next example with PyGeo, IDWAP, they're already in this component format. You already define their inputs, define their outputs, you can directly use them. So, which means that DAFoam also has an interface that rewrites the DAFoams as a component in OpenMDAO, and the code is written in here. This is the main new things in version 3. So to run the optimization with version 3, basically one need to have a run script that's very, very similar to this. We need to add a component, we need to define their connections, set up objective functions, set up design variables, and run optimize. And that's overall how it works. But here is just a very simple example to better illustrate this process. All right, if you no more questions, let me go to the next topic, which is aerodynamic optimization using DAFoam version 3. Here is the summary of this problem. It's an alpha problem. And the objective function is a CD, and the constraint is CL, the lift coefficient, thickness, volume, and leading trailing edge. This formulation is it's a standard tutorial in DAFoam, but in this case, we use a compressible flow case as the demonstration. How to run this case? Let's see. Let me go back to the. Let's exit. If you finish running the Docker, you can type this exits. You will exit the Docker. Let me see where I am. Okay, and in this OpenMDAO folder, but for this NACA 12 case, have to go to this folder, which is NACA 12 folder. Okay, and once you're in this folder, you can type ls. Well, I already run something, so I want to clean out the results. Okay, if you haven't run anything, this is probably what you will see. Okay. Then what's next? Once you're in this folder, you can use the command we just used to open the Docker. So let me see if I can find a command. Yeah, this is the command, which is in slide 11 to start the Docker image. So now you can see that I'm in the Docker container. I type ls and I'm in the right directory. And well, since that there's a typo here, this should be NACA 12 instead of there's a 1 here. Anyway, that shouldn't be a big problem. Then once you're in this folder, once you're in Docker, the very first command you need to run is preprocessing.sh. And then just copy this command and run this. When you run this command, you will essentially generate the mesh using the PyHip, which is a structure mesh generation tool we have. You will generate a very nice structure mesh. The mesh generation is done. And what's next is that copy and paste this command. This command will run this case using 2 CPU cores. Okay, when I run it, at the same time when it runs, it will also output the optimization progress to the screen. And you should be able to see it from here. In the beginning, we'll run some coloring. And after that is done, I'm going to explain the whole process later when we look at the run script. But now it is solving the CL because our target lift coefficient is 0.5. And because you just give some random angle of attack, this will not give you CL 0.5. So that's why before the optimization, the run script will find the correct angle of attack that gives you CL 0.5. If you look at this, now the CL is 0.5, and then optimization starts. First solve the flow and then solve the air joint, solve the flow, solve the air joints. You should be able to see the progress. Then how do we see the progress other than looking at the log here? We can go to another tab. It seems that you probably can't see my second terminal, which I need to share that to you right here. Okay. So this is my second terminal. I just need to go to here and go to workshops and go to 2022 summer. Go to samples, go to Nakanowo 12, and just let it run. Okay. So then the very first thing you need to look at is this file, opt_ipopt.txt. If I open this, you will see that, well, this case ran for, well, 2 iterations already. The objective function reduced from 1.6 to 1.4. So we have a good drag reduction. Okay. So I'm not going to let it run, but if you keep it running, probably it will converge in less than 20 iterations. We know that it's working well, and we have some progress. Yeah, it ran for 3 iterations. So this is same as before. So when you run it, it will be same as the version 2. I think the yes.
So I was trying to follow along, and when I try to generate the mesh, I'm getting a bad interpreter error.
So are you using the latest version of the Docker image 3.0.0?
Yeah, I just pulled it.
Okay. So are you using Windows?
Yeah.
Okay. So without knowing the exact error code, it's a bit hard to, if you can post maybe in a chat. Okay. See if you can
troubleshoot.
Yeah. So okay. Anyone has a problems run in this case, because I want you to have some hands-on experience by using the Docker to run it.
Okay, I'll put it in the chat. Thank you.
Yes. Let me, I guess while waiting, so let's see. Assume that you managed to run it and how to post-process the results. The post-processing will be same as before. So if you have the ParaView installed, you can just refer to this page, which we covered that in the last workshop. And we can use ParaView to visualize the shape changes. Let me see if I can visualize it. Although we only have 2 iterations, 3 iterations maybe, but we should be able to visualize it. Let me share you my ParaView. Here's my ParaView. You can just double click the ParaView.foam, which is in this folder. So just double, if you have already installed ParaView, you can just well, yeah, this file is here. Just double click the ParaView.foam. You should be able to open it in ParaView. You can hit apply. And then because we run this case in parallel, you have to choose on the left-hand side, the decomposed case. Then you hit apply. And then what's next is that you can use your mouse wheel to zoom in a little bit because the F4 is in the middle. And then on the top, you can choose which variable you want to visualize. Like this case, maybe I can look at the pressure. Okay, so you're seeing the pressure, I can zoom in a little bit more. And then you can hit this button on the top to play. You see that, well, we are at 30 iterations. You see some shape changes. And when you run it to about maybe 20 iterations, you see that get optimal design. Okay, again, the post-processing process will be very, very similar as before, which is not a focus of this workshop. Instead, I want to look at the next, it is N2 diagrams. If you remember, we have the look at an N2 diagram for simple problems. Now let's look at an N2 diagram for this aerodynamic shape operation, which is the very first thing after you have a neuron script. Make sure that this N2 diagram looks right to you. And how do we check that? Let me open this N2 diagrams in my web browser. And then I want to share that to you. Here's my web browser. Okay, this is the N2 diagram for this problem. Okay, of course you can click this to make it look nice, and I can move the equations and increase the font size a little bit. Okay, I guess this is better than before. All right, so in this case, we have many components. If you look at the sign color, Dvs component, mesh component, geometry components, we have a cruise group. And in that group, we have many other components. So what I want to do is that I want to correspond this to the slides we have right here. So let me first explain this diagram before we look at the wrong script. So as you remember, the main thing we set in the wrong script is defined how many components you have, how do you transfer data. So let's look at the component one by one. The first component is called DVS, which is the design variable component. And then in this case, we have a shape and angle of attack as the design variable. This is a very special component. It only has output, it has no input, because, and this is a component, if this, look at this, let me call this light green. This is dark green. So this light green is the output of a component. This dark green is the input of a component. So for the DVS component, it only has two outputs. We're going to use that as the design variables. We have a mesh component which contains this variable called x arrow 0. This is the surface coordinates for your mesh, which is also the output. You can choose this as the design variables, but you can choose to not use this as the design variable. In this case, we don't set this as our design variable because we just say that we have an initial surface coordinate as the input for this problem. And once you have this, let's look at this geometry component. This geometry component is essentially the PyGeo. If you use version 2, you know that what PyGeo does is that it uses some design variable as the input to compute the new surface coordinates. That's exactly what this component does. If you look at this, this component uses x arrow in as the input. Where does it get it? You can see that it get it from this mesh component's output, x arrow 0. Essentially, you use the initial surface mesh as the input. Okay, this is one of these input. Let's look at the second input for this geometry component, which is the shape. Okay, the shape essentially are the FFD coordinates. Okay, so which is our design variables, and it will be passed from the DVS component to the FFD component used as the inputs. Once you get FFD displacement, this PyGeo component, this geometry component will compute output 1, which is the x arrow 0, which is the new surface coordinates. It will also compute many other constraints. If you remember, PyGeo also compute constraint values. For example, what's your thickness, what is your volume of the mesh, and such and such. This component, essentially PyGeo, is already written in the OpenMView format. You can directly call it. I'm going to talk about that. How do we call this in the run script later? Then we go to this block. This block is called a cruise. We call it scenario, but essentially it's a group. It's a group of components. And because this is a dark blue, this is cyan. In this cruise group, we have arrow pre-component, solver component, and arrow post component. This arrow pre-component is ID1. If you remember, what ID1 does is that it receives the new surface coordinates as the inputs and use an inverse distance method to update the volume mesh, which is exactly what this component does if you look at it in this N2 diagrams. So this X arrow is the input of this component. Where does this X arrow come from? It's from this component. Okay, it's from the output of the PyGeo. So PyGeo give a new surface coordinates, give it to the ID1. Internally, ID1 will do some computation and output the DAFoam volume coordinates, which is the output. Okay, this is the ID1. Want to uncheck this? Okay, once ID1 has the new volume coordinates, we will give to the solver component. if you look at this, you will go to the solver component, and the solver component will also receive the angle of attack right here as the input, because the angle of attack is our design variable is directly from this design variable component right here. Okay, so in the run script, you need to set up this connection as well. Okay, and once the solver component gets the angle of attack, volume coordinates, we will solve for the DAFoam states, which is the state variable, and which is the output of the solver components, which contain the velocity, pressure, density, and such and such. Once you get the state variables, and this component will give this state variable to the last component, which is the arrow post. It's essentially this component will use the state variables, angle of attack, and the volume coordinate to compute CD and CF. And then in our optimization, we will use CD as our objective function. We will use CF as the constraints. You can see that the overall process is very, very similar to the simple tutorial we just did. Simple open-MDL tutorial. The only difference is that now we have much more complex components. Okay. Then what's next is that I want to show you the run script. How do we set that up? Well, probably we only have 3 more minutes before we go to the first break. Oh, that's fine. Now let's look at, well, I guess it's better to show you the slides here. So we just talked about the diagram, into diagram. Let's look at how do we set up this into diagram in the run script. So if you look at the right-hand side, this is a run script for this province. Import section has many more imports because most of them are from Memphis, because we already built this interface. We can directly use some predefined components for example, for DAFoam, for PyGL, for ID work, and such and such. And the second block of the code is the tasks. Well, let me set up something. We don't wrap it. And then this is the same as before. And this block basically defines the input parameters. If you have used version 2 before, you will notice that this is the exact same as before. We define the far field velocity, pressure, temperature, turbulence variables, target lift coefficient, angle of attack, reference surface area, and density, and such and such. And then we set out the DAFoam options. We set out the design variable surface, use the solver to solve it. And this parameter is for the flow residual tolerance. And this parameter is for the boundary condition. This is for the objective function. And this is Adrian equation options like the residuals and normalized states and design variable. This is the same as before. And again, the mesh options is also same as before because we're going to pass this option to ID. Now here's the main difference. We are going to define a class that will basically add all the components into this province. Well, it seems that we don't have time now. I suggest we take a 5 minutes break. We'll come back in about 5 or 6 minutes. Okay. Okay, let's resume. This is the second section of the 2022 DAFoam workshop. In the previous section, we talked about running an aerodynamic shell optimization using the new version 3. We talk about the N2 diagrams. Now we are looking at the run script. How do you set out the province? Okay, so on the left-hand side, I'm showing you the N2 diagram of this for this Nakadawa 12 case, which is the airfoil aerodynamic shell optimization case. On the right-hand side, I'm showing you the run script, the Py. Okay, so I already talked about that. The DA option here and the mesh options are very, very similar as version 2, but the one major difference is this top class, because we're going to define a class that adds components into this province such that OpenMVL can optimize it. So essentially, this top class, you can call it a different name, but it's just we call it a top class, inherits from the multi-point class. This multi-point class, which is defined in Memphis, which is essentially a group of components. Then in this top class, we need to define the setup function that in this setup function, we need to add all the components we have for this province. If you look at the left-hand side, which is the intro diagram. We have Dvs component, mesh component, geometry component, and many other components. We're going to add them one by one. So let's look at this line. But before that, I probably want to set out the line number. Okay. In line 105, we first create a DAFoam builder. So I'm going to explain what's this, but essentially it is the main entry point for the DAFoam component. So when you call this class, when you initialize this class by calling 106, what it does is that it will create a mesh, it will create a flow field, it will allocate all the memory that is needed for this problem. Then you're going to pass this DAFoam builder to many other components to let those components manipulate the data, maybe change the mesh, maybe change the flow field. So after this builder is created, and we add this Dvs component in line 109, so which corresponds to this component right here. Okay, this is an independent variable component. It's a very special OpenMDAO component that has only outputs. Then, but we haven't defined this output yet. We can define this output later in this configure function, but we need to add the component in the setup function. Then we go to this line 112 to add a mesh component, which corresponds to here. On the left-hand side, then we go to 115 to add geometry component. This geometry component is just essentially PyGL. That's why we need to pass the FFD files to this PyGL. If you use version 2, here is the place you give it the FFD file in the run script, which this geometry component is essentially here. Again, when we add this component, we haven't added any input and output yet. We can add that later. Then the next group or scenario is that, well, this cruise scenario, which is aerodynamic scenario, you can think of this cruise as a group of predefined components. It has ID warp, it has DAFoam, it has aerodynamic post. Okay, you just add this right here, and that's it. That's all you need to do. But of course, in this setup function, you can also set up some connections. Maybe it's better to show you through here. Okay, so right now what I'm doing is that I manually connect the output of the mesh component to the input of the geometry components. Let me show you how this is done. Just want to make sure that you can see it here. So the mesh x arrow 0 corresponds to the data here. The mesh x arrow 0. We want to connect this to this x arrow in for the geometry component. That's why we manually connect this. When you see a sort of gray box here, which means that these two variable has a connection. So if you don't set up connections, OpenMDAO will probably give you a warning that some input or some output are not connected. So very similarly, we need to connect the geometry x arrow in, which is this one, the geometry x arrow 0 to the cruise components x arrow, which correspond to here. Okay, so we basically set out this connection manually. So NFIS provides some automatic connection if the variables share the same name, but in this case, these two variables, they don't have the same name, which means that in this case, we have to manually connect. All right, after you add all the components, set up connection, we can go to the next configure this function. So let me go back to the diagram here. Okay, in this configure function, you can see that, well, it has quite a few lines here, but the first few lines, you probably don't need to change it. These lines from line 133 to 143, essentially add objective function you define in the DA options, get a surface coordinates, pass it to the PyGL to deform it, and create some triangulate surface for setting the geometry constraints. For most of the case, you don't need to change these lines. Starting from 146, and these and the following are case-specific settings. In the 146, and we define a class, or define a function called AOA, which is angle of attack, and essentially we define how do you compute the angle of attack, and the value. Oh, let me take it back. How do you compute the far field velocity boundary condition based on the angle of attack variables? The variable 0 is the angle of attack, which in this case will be our design variable. We just implement this. This is exact same as version 2. I'm not going to talk about this. After you define this function, you need to pass it to the cruise components by calling these two lines, okay, such that this cruise component, which is here, this component can use this angle of attack function. And then after that, we select some FFT points to move in 157, and this is same as before. Okay, if you use DAFoam version 2, you will notice that it's same as before. But if you use mark arrow with AD flow, you can see that the syntax is very, very similar. The only difference is that, and here the syntax, if you use PyGL, you call this add geo dv local, but if you use Enfys, you need to call self geometry component dot this function. It's just a slightly different name, but the overall logics are very, very similar. Very similarly, we can set a symmetric constraint because it's a 2DF case here. Again, it's very similar as before. The only difference is syntax for this function. And then in these few lines, we add the volume constraints by setting our leading edge list and trailing edge list. We add a thickness constraint, add a volume constraints, we add a leading edge constraint, trailing edge constraints. Again, these are the same as version 2. I'm not going to elaborate on this. So now let's look at 184. Once we set out constraints, which we set out these variables, what else do we need to do? Well, line 184 basically add output for the DVS component. If you remember, we added DVS component in the setup function, but we haven't had any output for it yet. That's why we added here. We say, okay, this component DVS has two output. One is called shape, which is this. The other is called AOA, is angle of attack. Okay, if you have more design variables, you have to add the name here. At the same time, you have to give the initial value for this design variables, such that optimization can start with these variables. And then once this is done, we need to manually connect the DVS output to the geometry and cruise, because if you don't connect them, and then the optimizer will only control this, but these two variables has no impacts for any of these other components, that really doesn't make sense. That's why we need to manually connect the AOA, which corresponds to this guy, this output, to the cruise.aoa, where the cruise.aoa is right here. So we create this connection right here manually, and also create this connection manually. So very similarly, we connect the shape, which is from this component right here. It connects to the geometry.shape, and this box, create this connection manually. So essentially, we are building this diagram line by line in this run string. Once you set our correct connections, you add the design variables, we have shape variables, angle of attack variables, set their upper bound and lower bounds, and then we can add an objective function, add a constraint function. In this case, we have many, many constraints. The way we refer to a specific constraint, we have to say the component name dots the variable names. For example, the thickness constraints, which is geometry component dot thickness constraints. Okay, we add thickness constraint right here. Okay, we self geometry. When you call this, by the way, when you call this line, you set a thickness constraint, also add it as an output for this component. But that's why we can set it as the constraint. And that's it. That's the top class. And we define something that is similar to the simple open MDL tutorial case, but of course, the syntax and the details, we have a lot more details. After you have defined this top class, the rest is very, very similar as before. We add this top class to the OpenMDL province and set out optimizers parameters. In this case, actually, we use IP-opt. And then we set up some debug options. We run the optimization. So because the default task is OPT, we first solve CL by calling this function, and then we run the run driver. So this is overall how it works. Any questions for this case? Let's see. Okay, so I got a question asking why this X arrow use a different name than this. Well, first of all, because these components might be developed by different developers, it's very hard to make sure that everybody uses the same name unless you work very closely. That's why sometimes you have to manually connect a component's output to another component's inputs. Okay, for example, this NFIS interface allows you to combine different code. For example, you can combine OpenFOAM with ADFlow. You can combine a VLN code with a structural solver, for example, text. So you can imagine that it's very hard to ask everybody to use the very consistent input and output names. So that's why sometimes we have to manually connect it. Hope that answers your questions. All right, let me see if I have. Okay, so I got another question asking, how can we define deformation in different directions, like the shape variables in Y? So let me show you where this line is. So if you remember in version 2, when we add a design variable, we use this add GLDV local. We can prescribe an X. So in this case, we can just say this axis equals Y. By default is Y, but if you want to change it to Z, that's okay. And depending on the case, you just add this here. Okay. So if you're not quite sure what's the syntax for this key, you can always search for this function in the NFIS repository. I think I have shown you the open source, the address for the NFIS repository. Okay, great. Any other questions? You can either unmute yourself or just type it in the chat. I should be able to see it. All right, if no more questions, so we're gonna quickly summarize this case. So in summary, you can see that the run script is essentially an OpenMDL run script. So we suggest you first learn how OpenMDL works by going through the documentation. So we can use this script to run any airfoil aerodynamic mesh optimization with V3. If you want to change anything, just refers to FAQ. This was written for version 2, but they also worked for version 3. You can see that the only difference is just some syntax difference. And if you want to run the 3D case, we have a tutorial here, or a multi-point case, we also have a template for that. And that's all I have for this aerodynamic mesh operations. Bernardo, are you there?
Yes.
Okay, so what I'm going to do is I'm going to unshare myself, and then maybe you can share a screen to talk about the aerostructure operation.
Perfect. Thank you, Ping. All right. Is everyone able to see my screen?
Yes.
Perfect. Okay. So building off of what Ping has just talked about, I'm going to go into aerostructure optimization. So that is combining DAFoam with some other solvers using this MFIS framework and OpenMDAO. So this will be the outline of this section. We'll start with what is aerostructural analysis and optimization. Then we'll go into how do we couple disciplines and solvers. How do we set up an aerodynamic problem and a structural problem? How do we combine them? What does this run script look like? So we'll go over something similar to what Ping just did in the last section with the run script. And then what does the problem look like represented in OpenMDAO? So we'll look at an N2 diagram. And then what do aerostructural analysis and optimization results look like? And we'll open up peer review to go over how to post-process the results once you have the case run. So in broad terms, aerostructural analysis is when you combine aerodynamic and structural analysis into one. So what you're looking at here is an example of this. The grayed out or the translucent wing design that you see in this figure is the original undeformed wing that we ran CFD on. But we know that when a wing is under load, it will likely deform in real life. So with each CFD run, every time we do an aero analysis, we'll also run a structural analysis, and we'll apply those surface loads onto the structure to deform, and then we'll apply that deformation back to the aero mesh. So what you see with the boundary mesh here with the wing and the symmetry plane and the contours of coefficient of pressure, you see that the wing has deformed through the analysis, and this is a converged aerostructural analysis. Now, when looking at this in terms of the different disciplines and solvers and components that we need, This is what we call the extended design structure matrix. For aerostructural, there are a couple of different segments to it. You start off on the top left with this pre-processing stage that's marked in green. And you start with a baseline design. You come up with the freeform deformation grid of points that are going to parameterize your design. So in this case, a wing. You come up with your aerodynamic mesh and a structural mesh. And all of that is passed into these geometry parameterization and volume mesh deformation components. And that's the pre-processing stage of the aerostructural part before you get into the actual solver. Now, this case setup is passed into the aerostructural solver. That's this somewhat circular block here in orange. And this is what's responsible for converging the aerodynamic solver with the structural solver. So that's what's going to do the two-way coupling. The first part of this is retrieving these aerodynamic surface coordinates that may be deformed, for example. And this deformation could come from an update in the design during optimization or the deformation from the structural analysis. So at the beginning of, or before we run the aerodynamic analysis, we'll deform the surface and the volume mesh to make sure that our CFD mesh accurately represents the surface that we need to simulate, or the volume we need to simulate. We'll then run a flow solve, and we'll compute the surface loads or surface forces over the wing. And then we'll pass those into our load transfer tool. So we'll take those loads and we'll project those, what are essentially point forces, onto the structure. And then we'll run a structural solver with those structural loads and compute a structural displacement. And that displacement is passed back to this aerostructural solver, which updates the aerodynamic mesh with the new displacements and runs this again until you can think of it as the aerodynamic mesh and the structural mesh are coincident and they have converged in a two-way coupled way. Then once this chunk has converged on the bottom right, we'll compute the coupled adjoint. So we'll compute the derivatives of both the aerodynamic and structural solvers in the case, and then we can compute what the next design variable values should be. So we'll go to the next iteration. So when looking at this diagram, you can think of aerostructural analysis or aerostructural optimization as progressing from left to right diagonally, and some repeated iterations within this aerostructural solver before updating the design variables on the next loop. Are there any questions so far about how this is defined? Great. Okay, we'll move on to the next section. So how do we set up the actual subproblems for aerodynamic and structural analysis? On the left here, we have an aerodynamic setup. The convenient thing is this is no different from, for example, the airfoil case that Ping just described. You come up with your mesh for DAFoam, and you come up with a freeform deformation grid. So here we see what was originally a structured mesh with pi hip, but it's turned into a DAFoam mesh for the what we call the mock tutorial wing. And we have a FFD grid on top of it with the red dots. So the aerodynamic mesh and FFD are no different than a typical aerodynamic optimization case setup. The structural mesh here on the right, this is a what you might consider a typical wing box. It has skins, spars, stringers, and ribs. And you can come up with this either with, in the MDO lab, we use a package called PyLayout, or you could use something like Pointwise or even iSim to come up with a structural mesh. Now, the one note that I'll add here is that it's very important that when you do come up with these meshes, they are coincident in the global reference frame. So however you define your wing box, it should actually align with the wing. So if you were to put these two images together, you would see that that wing box is actually within the wing in the CFD mesh. So this, yes.
Oh, we have a question in the chat. Can you answer
yes.
that?
Primary solvers are decoupled, but the adjoint one is coupled. Let me go back a slide. So I'm not sure what you mean by the primary solvers are decoupled. The aerodynamic solver is run first, and then the aerodynamic loads are passed to the structural solver. The structural solver is run, which computes some sort of displacement on the wing box, and that displacement on the wing box is passed to the aerodynamic solver. So the aerodynamic mesh is updated and deformed, and then you run the CFD again. So the flow solve is also two-way coupled, not just the adjoint. Does that answer your question? I'm sorry, I'm not totally following what your question is in the chat. The adjoint is coupled and the flow solvers, the flow solver and structure solver are also coupled.
Actually, thanks for the presentation, first of all. Am I audible?
Yes.
Okay, so I have seen some of the structural optimization, which actually has a coupled implicit solver. So they have a whole matrix which actually solves for the aerodynamic problem, including the structural problem. So I meant if this is the same case for your solver as well.
In this case, we do it sequentially. So we use something like a Bloch-Gauss-Seidel to first compute, Bloch-Gauss-Seidel method to first compute the aero side, and then project it to the structure, and then update aero, update structure, and so on and so forth. So the solvers aren't coupled internally, but they're coupled with OpenMDAO, and using a Bloch-Gauss-Seidel method will iterate and to converge the two.
Okay. Thanks.
Does that make sense?
Yes.
Okay.
Thanks.
Perfect.
One quick thing to add is that the adjoint is solved in a very similar way. We solve the adjoint for the aero solver, and then to solve the adjoint for the structure solver, and then repeatedly solve it using the Bloch-Gauss-Seidel method, and until both of the adjoint residuals are very, very small.
Right, and we'll get to how to define those solvers in the run script in a few minutes as well. So this is how you do the problem setup, and just remember to make sure that when you do the case configuration that everything aligns properly, so that your meshes do overlap as you intend them to, even though they are two separate simulations. So we'll go through what we call the mock tutorial optimization case. This is something that's publicly available online from the MDO lab. In this case, we'll show how to use it with DAFoam and MFIS. So the problem is using DA-Row simple foam will optimize this geometry called the mock tutorial wing. And the objective function is the coefficient of drag. We have 7 twist design variables based on that FFD box, 96 shape design variables, and angle of attack. And the constraints will be coefficient of lift of 0.3. We'll make sure that the wing box doesn't fail by computing the von Mises stress failure condition. And then we'll also have some thickness, volume, and then trailing edge and leading edge constraints. And just to give some context to the physical parameters, the flow speed is 100 meters per second. And then for turbulence model, we'll use the Spalart-Almaras model. You can find, if you want to follow along, you can find the case setup in the workshop repository under Aerostructural. So we'll go through the run script in a similar way to what Ping did earlier. I won't pull it up in the terminal, but we'll go through it here as it's copied into the presentation. So as with the airfoil case, there are quite a few packages that you need to import to be able to use DAFoam with an MFIS. These are roughly the same as before, with the addition of the ones needed specifically for load transfer, displacement, and structural. So what we're looking at there is we need this tax package that is our FEM tool, and we'll also need this meld package, which is the next one down, and that handles our load and displacement transfer that you need to go from DAFoam to structure and back. Now we'll go into the DAFoam options. As you see, this is very similar to what you might expect from a normal DAFoam aerodynamic only optimization. This is because when we're defining the DAFoam component, it is separate from the structural component. So you define it as you normally would. So on the top here, we define the free stream parameters or important quantities of interest. So free stream velocity, pressure, viscosity, temperature, target CL, and then angle of attack, density, and reference area. The one very important thing to note is when passing these to the DA options, there is an additional dictionary that you need to provide to DAFoam. And this is called FSI for fluid structure interaction. And when you're running the FSI side of DAFoam, when you compute surface forces, you need to account for the fact that there is some reference pressure that is offsetting the forces on the surface of the wing. And so here you need to specify what that reference pressure is. And usually it's sufficient, for most cases, it's sufficient to simply call PREF and provide the value that is the free stream value that you've provided here. And that makes sure that you don't have some sort of offset due to the free stream pressure in the flow. Now, defining the functions of interest, you do this in exactly the same way as you do for the aerodynamic only case. So for example, here for CD, you'll define it as a force with patch to face source, you'll select the wing as the patch of interest. The direction will be parallel to the flow, and that'll be based on the alpha AOA, the design variable we define. You can scale it however you'd like, and then you would add it to the adjoint to compute gradients. And you'll do the same for coefficient of lift, where you'll define it as a force, again, patch to face, and you'll select the wing. In this case, it's normal to the flow because we want it to be the lift direction. And you'll again select the angle of attack and scale it how you'd like, and then add it to the adjoint. So this is no different from what you have done in the past for DAFoam V2 and what you would be doing for an aerodynamic only case in DAFoam V3. The adjoint equation options and state normalization is very similar as well. So these are some typical options that you might use, PC fill level or jackmat reordering. There are two here that are important. The first one is GM-res relative tolerance. How this normally works is DAFoam will compute the adjoint a single time for aerodynamic optimization. So you'll compute your gradients, you want to converge this to something very tight, for example, all the way down to 1e minus 8, if not even further. But when you're doing aerostructural, when you're running a coupled aerostructural optimization, it will iterate on these derivatives with the structural derivatives as well. So what we found is that you can speed up this gradient computation by giving a looser relative tolerance here that will be run repeatedly for several iterations of that coupling with the structural solver. So eventually, just by setting 1e minus 2 here, you might eventually get to an absolute tolerance of 1e minus 10, because it'll say 4 times, it'll iterate and go minus 2 each time. And along with that, it's very important to set this use non-zero initial guess to true, because this will speed up how the adjoint is solved, because you'll use the previous guess in the previous iteration, which is much better than a 0 initial guess. If you were to set a very tight tolerance above and set this parameter to false, the optimization would still work, but each adjoint, each coupled adjoint would be much more expensive because you would be converging every single iteration from scratch, instead of leveraging the fact that you can repeatedly go closer and closer as you iterate with the structural derivatives. The normalized states are the same. So you can set those essentially to the free stream values for velocity, pressure, temperature, and then you can use something around the same order of magnitude for viscosity. Now, something that has come up with aerostructural analysis and optimization, and something that perhaps some of you have run into in DAFoam, if you're using something like Snappy Hex Mesh to generate your meshes, is mesh failures. Now, when you're doing aerostructural analysis and optimization, you're deforming the mesh twice. So that is once when you actually change your design variables, so if you change the shape or the twist, and you also change the mesh when you're deforming the mesh under load, when you get the displacements back from the structure. And this means that in some cases, the mesh can be poor quality. And so what you end up with is a lot of failed cells. But what we've seen is that some of these cells can still be used for analysis accurately. So what you may want to change, if you need to, is these check mesh thresholds. These are 3 parameters that we often change: the max aspect ratio, the max non-orthogonality, and the max skewness. We don't recommend you change them to anything ridiculously loose in terms of tolerance, because then your analysis may fail, but you may want to give DAFoam a little bit more leeway in terms of this mesh check, so it doesn't immediately reject a design that is feasible and may be better or more optimal than the previous design. Now, something that's very important with MPhys and the new DAFoam version 3 as compared to before is there's this design variable dictionary. In this design variable dictionary, which is passed to DAFoam in the options, you need to define all of your design variables. So here we're defining the angle of attack, AOA, and we define what type of design variable it is. We say what patch it applies to, the flow axis and normal axis. We define the twist design variable as well, and the shape design variable. And those ones are a little bit more simple because they're simply FFT design variables. It's critical that you define design variables here, because if they're not defined when passed to DAFoam as options, it's very likely that they will not be connected properly within your problem setup, which means that your case will simply not work. So always be sure to check that your design variables are defined within your DA options. Now, once we've completed our DA options, you need to specify the OpenFoam mesh. And because OpenFoam mesh is essentially an entire directory, we do that here with this mesh options. and we just define that the current working directory is the grid file. And we'll call it OpenFoam, and then we'll define the symmetry plane. So that's a point, and then also the normal vector for the symmetry plane as defined here. So that completes the DAFoam specific setup as we're setting up the options and defining the mesh. Now we flip to tax, which is our structural solver, and we need to define how we set up the structural problem. So that will import what we have as this tax setup file. If you were to look at the workshop file, you see that there's an additional Python script that we use for setting up tax. And we set up these options. So an element callback function, a problem setup function, and we define the mesh file, which is this BDF and ASGen file. Now we'll go through what this tax setup file looks like in the next slides. So I have here in red that, just to make note that this is actually a separate file from the run script itself. You could include it in the run script if you wanted to, but we have it organized separately in the workshop files. But this chunk here is from that tax setup file. So you start by importing the package tax, as well as some of the classes that you need. So elements, constitutive, and functions. And then we'll define the material properties. So for this case, we're just using conventional aluminum material properties. And then you can define the shell thickness. We're using shell elements, so we'll define the thickness here. In the first function, the element callback function, will define what our elements look like. So this is a function that we need to provide to tax, which has roughly this structure. So you need to maintain this for any aerostructural case you do. And inside of it, we define the material properties using the properties we defined before. We define that it's a shell element here, and then we add it as an element. So we return that as an element to the structural solver. We also need to set up a tax problem. So this is defining any function of interest or any additional structural loads. So we define this problem setup. Again, it needs to follow the similar format so the tax can recognize it. And we define inside of this a problem.add function. So we add mass. So this is how we get the structural mass if we were, for example, trying to minimize the mass of the structure or at least constrain it. And then we can also add a function for the KS aggregated von Mises stress failure. So this is essentially taking the maximum of the von Mises stress failure condition over the entire wing. And that will be returned as a value that you could use as a constraint to ensure that your wing is not going to fail, for example. And finally, we can add, for example, gravity as an additional load on the system. This could be anything. This could be a propeller load pulling on the wing or something like that. In this case, we'll just use gravity that's acting down on all of the elements across the wing. So now back to the run script itself, we'll start by defining the Dvs component. So this is similar to what Ping described earlier. We have this class that's a multi-point class, and this is where we define all of the components for the Dvs case and for OpenMDAO. Now this chunk that I have here shows the different subsystems that we're going to use. So at the top, we have an Aero subsystem. So this is Aero Builder. So just as before, as Ping showed, this is the DAFoam builder, and you provide the DAFoam options, the mesh options, and you define it's an aerostructural scenario, and you initialize this builder. Along with that, you can define you should define the aerodynamic mesh component, and that's what we do here with mesh aero. So you get the coordinate system from DAFoam to get the aero mesh. Now we do the same for tax. So we take the structural builder and we define the tax options, and we initialize it, and then we get the structural mesh, just like we did for DAFoam, but in this case for the structural side instead. And finally, the coupling between the two is this transfer scheme, which is using meld as we defined earlier. And this meld builder takes in the aero builder, the structural builder, what direction is your symmetry plane, and then you initialize it. And now you have the aerodynamic component, the structural component, and the communicating component between the two that takes structural loads and passes them, structural loads from the aero solver and passes them structure, and takes the structural displacement and passes them back to the aero solver. The next part is to set up some additional components and solvers that you need within the Dvs problem. So we'll start by adding a subsystem called Dvs, and this is just an independent variable component. All this is it allows us to specify design variables and broadcast them to different components within our Dvs problem. And we'll see this later when we open up an N2. With that, we also define a geometry component. So this is using dvgeo, as you may have used before. That's the same mock package, but it's it's defined within MFIS or wrapped in MFIS. And this will take in the FFD grid so that you can parameterize your wing. And once we have all this, we have all the components that we need. We just need to connect them so that we have everything communicating as intended. Now, as we discussed before, there has to be some sort of coupling solver between aerodynamic and structural analysis. And this is where we define that solver. So we define a nonlinear solver. This is this nonlinear block Gauss-Seidel, and we define the options that we'd like. So for example, max iterations of 25 to do this coupled solve, and a relative tolerance of 1e-8 and absolute tolerance of 1e-8. And you do the same for a linear solver, which is this linear block Gauss-Seidel. Again, you could do a max iteration of 25 with a relative tolerance of 1e-6 and an absolute tolerance of 1e-6. So the nonlinear solver is what controls the convergence, or it controls the aerostructural primal solve, as we discussed earlier. So they're not coupled, as was asked, they're not coupled internally as a solver, but this nonlinear block Gauss-Seidel is run instead, and you iterate on that until the two converge. The linear solver is instead responsible for computing gradients. So that is what does the iterative approach that we spoke about, that will converge the gradients once you have already converged your aerostructural primal case. Once you have all these components defined, you take an MFIS scenario. In this case, we'll call it cruise, and you'll add this aerostructural scenario aerostructural. And for this, you need an aero builder. In this case, it would be DAFoam. You'll take a structural builder, which is for us tax, and then a load transfer builder, which is the load transfer builder that we define. So now we're providing to this aerostructural scenario all the components that we defined. And with this, we'll also specify that we want this nonlinear solver that we defined, as well as the linear solver. So with this section here, we've provided to MFIS the information that we want to run an aerostructural case, and these are the parameters that we're going to use for each of the solvers. Now it's time for us to connect all of the different variables now that we've defined those solvers. So first we'll connect the aerodynamic and structural solvers with both the geometry. So we'll connect the geometry component to be able to provide those design variables to the aero and structural components. This is what I was mentioning, that we're taking a single design variable group and broadcasting it to both the aerodynamic side and the structural side. So that's what that's what is happening here at the beginning of this chunk. We'll then add any structural DVs that we want. So those are, for example, the thickness, and we can add this output to our design variable group. dvs.addOutput will add the structural design variable, and here we'll specify an initial value. So here, for example, we're specifying an initial value of 0.01. And we'll connect this structural dv underscore struct, to cruise dv struct, and we'll provide that to tax. A few more manual connections we need to make. We need to connect the aero mesh with the geometry. So we'll make that connection here, and we need to connect the structural mesh with the geometry mesh as well, so that there's a connection between the geometry group and then the respective points on the aerodynamic component and the structural component. So these are, you don't need to worry too much about these as long as you make sure to include them. They are standard through all of the aerostructural cases that you may run. So once we've finished the setup method, we go to the configure method. Something that's very important is to include this configure call at the top here that I'm highlighting. This will make sure that everything that you defined in your setup is propagated through to MFIS. So do make sure to include this configure call at the beginning. Now, the next step here is to define the functions that we specified in the DAFoam options. So here we'll have this MFIS add functions. So for example, we had coefficient of lift, CL, and coefficient of drag, CD. And those two, once we specify this call, will get propagated through to DAFoam and specified as functions of interest that we can connect to as objectives or constraints. We'll then get the points of the surface coordinate from DAFoam. So this is all of the surface coordinates on the wing, for example. And then we'll also add this point set to the, for DAFoam, we'll add it to the aero side, and then for tax, we'll add it to the structural side as well. So we're just adding the point set that we retrieved from the surface mesh that we were using before. And then we can get, for example, the triangulated points from the geometry component if we need to do some sort of constraints. So now it's time, as we did before for the airfoil case, to define design variables. So as you likely have done in the past with a DAFoam case, you will define design variables exactly like you did in the past, just with slightly modified function calls. So we'll start by defining a reference axis for the twist variable. So you'll call the add reference axis, and you'll define what you want the name to be and what location along the wing it should be at. And you'll define the axis in which that reference axis should be oriented. And this new reference axis can then be used to define a twist variable. So that's what we're looking at here, that it defines this twist along the FFD box. And we can finalize that by adding this to the geometry component, by adding this twist variable and providing an initial value with the function that we specify above. So this is how we would define a twist variable for an optimization case. If we want to define shape as well, we can retrieve the points in the geometry and specify, as for example, Ping did in the airfoil case, that we want a shape variable. The angle of attack is a little bit different. Those who have used DAFoam in the past are probably familiar with that. The angle of attack is not a geometric design variable. It is a flow design variable. So it goes directly to DAFoam as opposed to passing through a geometry component. What we'll do is define, similar to the twist, we'll define a function that computes or changes this angle of attack or the free stream flow. And it will update DAFoam every single time it is called. And what we need to do is add that as a solver function as well as a post-processing function. So once you define this angle of attack function, you'll add it down here with cruise, coupling, arrow, solver, and then add dvfunc, AOA, and then the objective, the function that you're providing. And then for this, the same for self, cruise, arrow, post, and then add dvfunc, AOA, and again, provide this function. Now it's very important that you do this, otherwise DAFoam and MPhys will have no knowledge of this angle of attack variable and they won't know how to compute it, even if you specified it before as a design variable. So be sure to include this function as well as the add dvfunc. Now it's time to configure all of our constraints. And again, just as before, these are very similar to how it was done in the past with DAFoam. So if you're experienced with DAFoam v2, you probably are familiar with this already, but we'll define a leading edge list of points and a trailing edge list of points, and we'll provide those to do a thickness constraint and a volume constraint. So this ensures that, for example, our wing does not become entirely flat during the optimization. And then just as you may have done in the past, you have these calls to add thickness constraint, add volume constraint, add leading edge, trailing edge constraint. And again, for the first is leading edge and the second is the trailing edge. So again, nothing here has changed from the previous version of DAFoam, just the function calls a little bit. So you have to familiarize yourself with these new names. Now finally, it's time to add the design variables themselves. So again, we'll reference that independent variable component I spoke about earlier, and we'll add some outputs to that. And that's where we'll control our design variables. So the first one being twist, where we set this add output to the DV design group or the component. And we'll set some preliminary values here. We're just setting them to 0 with the number of twist sections that we've defined. And we can do the same for the shape variables, where we'll set all of the initial shapes to 0, knowing that we have, in our case, 96 shape variables to begin with. And finally, we'll also add angle of attack, which is just a scalar, and we'll define that as what our initial angle of attack would be for the optimization. Now we need to connect everything, because so far these twist, shape, angle of attack variables are not actually connected to anything within the MPhys problem. So we'll connect twist to the geometry component twist, which is already connected downstream to the arrow and structural solvers. The same goes for the shape. So we're connecting to the geometry shape component, which goes downstream to the arrow and structural solvers. And then angle of attack gets connected directly to, this is the DAFoam component, because that does not need to go through the geometry component. Once those are defined, we can tell MPhys and OpenMDAO specifically that these are design variables. So we have a call to add design variable, and we can define a lower bound, an upper bound, and if we want to scale this value, we can add a scalar as well. So this is if you want to do some sort of problem scaling to make sure that all of your design variables are on the same order of magnitude, for example. And with this, we've now defined all of our connections for design variables and told OpenMDAO and MFIS that these are design variables that it needs to use for the optimization. Finally, we'll define the objective and constraint functions. So as we mentioned before, our objective is coefficient of drag, CD, and that's what we've defined here. So we've told OpenMDAO with this add objective call that we want to connect to the DAFoam within cruise, the post-processing, which computes the function, and then within that, the coefficient of drag. And as we're setting the lift constraint, we can do the same. So we call the add constraint function, and we specify CL within the arrow post tool. And in this case, we'll set it to our constraint, which is 0.3. And again, we can define some sort of scaling value if we'd like to. We can repeat this for each one of our constraints. So the next one is a structural constraint, which is that aggregated von Mises failure constraint. We have a thickness constraint, the volume constraint, and then the leading edge and trailing edge constraints. So you're just using this add constraint function and specifying what the values either are bounded by or equal to for each of these conditions. So that wraps up the configure method for the aerostructural problem. And now we just finalize our OpenMDAO problem setup. So you define an OpenMDAO problem and you use the model that we previously defined, which we've called top, and you call setup. So this is what will run through and configure your entire problem and make sure that everything is connected properly. The next line sets up an N2 diagram, which we'll look at in just a moment. And this will output to, in this case, MFIS aerostruct, so you can visualize all the connections. And it's very important to do this to make sure that you have everything connected as you expected, because in some cases it won't necessarily throw an error, but your design, without realizing it, won't make any sense because something is not correctly connected. You can then add these opt funcs with DAFoam, so you can initialize the optimization function and then specify some properties for example, setting the optimizer, setting some parameters or settings for the optimizer. In this case, I'm showing it for SLSQP. And then you can also set some properties for how the optimization driver is run. So for example, debugging, or if you want a history file, here we call it opview.hist. So this is how you define sort of the macro parameters for your optimization case. Finally, when you're actually running this case, just as a lot of the other DAFoam tutorials have, you can specify different tasks. The default task here is opt. And so this task will find a feasible design, and then it will run driver, which means run the optimization. You have a couple of different options. You can also just run primal, which will run the model once and not any optimization. So it'll just compute that coupled error structural analysis and output the result. You can also run the adjoint alone to compute the total derivatives, or you can check your derivatives to make sure that your derivatives of the objective functions or constraints with respect to design variables make sense. If you're having trouble with analyses, it could be a useful check to make sure that your gradients are not incorrect. So now that we've gone through all of that run script, the resulting N2 diagram is what you see here. Now I'm going to open this up in a web browser instead so that we can visualize what it looks like. It has a fair bit more to it than the airfoil case, for example, just because there are a lot of additional couplings that don't exist in aerodynamic only. So for example, on the top left, what we have here is we have a DV group. So this is where we have defined our twist, shape, and angle of attack. And that feeds into the geometry group. So this geometry group handles all of the mesh information. So X arrow in, X structural in. So those are coordinates for arrow and structural mesh, the twist, the shape, and then these are all the outputs that come out of the geometry group, including the thickness constraint, the volume constraint, and then leading and trailing edge constraints as well. Now, we have our cruise scenario, which is what handles all of the computation for the aerostructural case. So this cruise scenario wraps a structural preprocessor, the actual coupling between the aero and structural components, and then the aero postprocessor and structural postprocessor. So looking at the coupling component, if you think back to that XDSM extended design structure matrix diagram we were looking at, you can think of the different components. So we have the geometry displacement of the aerodynamic mesh. So we take in our X aerodynamic mesh and the displacement from the wing box, and we provide a new X arrow, which is this new new set of coordinates for the aerodynamic mesh. And then we'll provide that to the aerodynamic solver, which will solve the flow and compute forces. And these forces are then passed to a load transfer scheme, which are passed to a structural solver. And this structural solver is passed back to this displacement transfer toolbox, which then repeats the process. So what you can think of is we start at the top left of this coupling, and we move all the way to the bottom right, passing data from left to right with these red lines, and then going all the way back to the beginning, following this green line, and we'll repeat this until the aerostructural coupling is complete. After this, we have the aero post-processing. So once that is the aerostructural analysis is complete, we can compute the CD and CL for that converged result. And we can also compute any structural post-processing that we'd like. For example, we specified the mass and the von Mises failure condition. So as I mentioned, always take a look at this N2 diagram because it gives you a way of visualizing to make sure that everything is connected and makes sense. So here we can see that everything is connected as we might expect, and we see data flowing from top left all the way to the bottom right with this coupled or repeated analysis block here. And one additional note is that on the right, we can see the solvers that we're using. So I mentioned the nonlinear block Gauss-Seidel, which is shown here in this greenish color, and that is what wraps this coupling here. So that's how you're doing your aerostructural solve, and that's what's shown in this N2 diagram. So that'll switch back to the presentation. And this is what your final results might look like. The top is the baseline analysis. Here we have an exploded view. Of course, in the simulation, these are all coincident, but we have on the top is the ribs and stringers shown with the von Mises failure condition value, and then the skin surface as well in the middle, and then contours of coefficient of pressure on the bottom of the baseline design. And now on the bottom of this slide, you can see the optimized design where again, we have this exploded view, and you see that the stress is a fair bit lower given the optimization that we ran, but still concentrated roughly in the same spot. And you can see that maybe a little bit hard to see over the slideshow, but that the wing design the aerodynamic shape has changed quite a bit, and the contours are fairly different. In this case, it was a single point optimization, so the leading edge of the wing is quite sharp, but it's just an example to show how to run this case. I'm going to switch to ParaView so that you can see how you might post-process this case. And I'm using ParaView because it's open source, but you could also do this with TechPlot as well, for example. So once you've opened up ParaView, you should open up the DAFoam case. So in this case, I have it saved on my desktop, and I'll open up ParaView.foam, and this will open up all of the DAFoam case. So I'll specify that I want to look at the symmetry plane and the wing to not see too much of the mesh, and the case is already reconstructed, and I'll go ahead and hit apply. And when we look at these results, we see we have the wing that we were just looking at. And if I were to include the first time step, this is the baseline design without any contours. And instead, this is once we've run this is analysis only, not optimization. Now we're interested in also seeing the wing box itself. And so we have post-processed the wing box structure as this cruise VTK. TAX will output a cruise 00 object. So we have the VTK version, and we can load that right into ParaView as a separate object. So if I were to hide the OpenFoam case, I can look at this wing box, and I see here that we have contours of, now I'm showing U, which is displacement in the X direction. You could also do displacement in the Y direction, which is the movement vertically from the wing, or the failure condition, which is what we're most interested in. So this is a similar plot to what I had in the slide, just showing the failure condition over the wing. Now, in pair review, when you show the aerodynamic mesh, you'll see that there's a discrepancy between the mesh from the Aerosolver and the structural mesh. And this is because the Aerosolver is given these updated coordinates and the mesh is deformed. So the aerodynamic mesh that you see on top is a true deformed mesh. The structural solver is just the baseline design without any displacement. If you want to see the structural displacement as well, what you can do is select this cruise object and go to filters within pair review and scroll all the way to the bottom and select warp by scalar. Now you have to do this one component at a time because it's imported without seeing it as a vector, but we'll take the U component and we'll specify that that's in the X direction. We'll hit apply. We'll do that again for the Y direction, the V component. And you can do it once more for the Z component. And you'll notice that when you then show the DAFoam mesh, they are coincident. And so we can show, for example, failure on the structural mesh. And I can go ahead and change the color bar on one of these so that we have the von Mises failure condition here and the DAFoam mesh. So this is a way of post-processing your results in pair review. Something similar can be done in TechPlot if you prefer that instead. So with that, I'll switch over to summary. So for yes.
A quick question. Can you also show us how to generate this VTK? I guess the text does not directly output this VTK, right?
Correct. So if I were to look at that is something a little bit tricky to describe because I'm on a Mac and Tax does not run on a Mac, but I can at least describe the process. So when you run an analysis, your directory may look like this. And what Tax will output is a cruise_00.f5 file. And this .f5 file is not readable by TechPlot or pair review or any other tool to my knowledge. But there are some built-in functions within Tax that allow you to convert this F5 file. So if you look at the Tax documentation, which I can post a link after this in the chat, or some instructions elsewhere on the DAFoam website, you just simply run that utility, and it's called F5 to either VTK, which goes to pair review like we're using, or F5 to Tech, which goes to TechPlot, which is this PLT plot here. So I can't show it because I don't have that running on this computer, but it's just a one-line command that will convert all of your F5 files, if there are multiple, into visualization files that you can use for TechPlot or pair review.
Yeah, sounds good. We will probably add that line to these slides after the meeting.
Sure. Yes, we can add that here. So as a summary, for aerostructure analysis and optimization, we've coupled DAFoam with Tax. This is a flexible open source finite element solver, and it's available from the SMDO group. You'll also need MELD as well, which is available from the same group. This is all available on GitHub, open source. We have leveraged OpenMDAO to manage all the solver coupling and data passage. So this is meant to really streamline the configuration for the user and make it so that if you need to add an individual component somewhere, it should be easy. And it's just a matter of adding connections as necessary. As with before, for the airfoil case, the run script is largely just an OpenMDAO component. So you can define your optimization and scenario or scenarios if you're doing multi-point, and the problem options intuitively with the guidance of, for example, the OpenMDAO documentation. So with that, I'd be happy to take any questions about aerostructural analysis and optimization, or pass it back to Ping for the next section.
All right, thank you, Bernardo. If no questions, I guess we need to take a 5 minutes break. We'll come back in 5 minutes. All right, welcome back. This is the third section of the 2022 DAFoam Workshop. And the last two sections, we talk about the new features in DAFoam version 3, along with OpenMDO tutorial and the aerodynamic share optimization example. In the last section, Bernardo talked about aerostructure optimization. Now, in this section, we are going to talk about how to add new features for DAFoam. If you just want to use DAFoam, probably you can skip this section. But if you want to add a new feature, such as, for example, new parameters, a new function, a new objective function, that we will talk about how to do that in this section. So here's the outline. So I will start with the overview of the source code structure. But before that, we got a questions from the previous section that I guess Bernardo already answered the question there. The question was that how to get the mass for aerostructure optimization during optimizations. I guess if you set a mass as a constraint objective function, it will be printed to the screen. But as Bernardo mentioned in the chat, that if you somehow don't see that in the screen on the screen, that you can use this get value function to get the mass from the optimization. Okay. All right, let's look at the source code structure overview. If you look at this, this is the main code structure in DAFoam. We have 3 layers: OpenFOAM, Sizen, and Python. So the OpenFOAM layer essentially is written in C++. It contains some libraries. These libraries are pure C++ libraries, which are not directly callable from Python. But as you know, that when we run optimization, we use some Python script. That's why we need to develop this Sizen layer to basically wrap all these OpenFOAM libraries into some Sizen libraries, such that the Python layer can, for example, your run script can call these libraries during the optimization. This is from a very high level. That's overall what's the code structure for DAFoam. Of course, I'm going to elaborate on these 3 code layers in the next few slides. So I'm probably going to go back to this diagram later. But just keep in mind that we have 3 layers. Now, the OpenFOAM layer overview, that, as I mentioned, that this layer contains C++ class, and for the OpenFOAM primer solver and the Adrian classes to compute the derivatives, to solve the flow, to compute the partial derivatives, compute the total derivative, and such and such. And the source code is in this directory. Okay. So when we compile DAFoam, when we run the all-round scripts, it will compile dynamic libraries for 3 conditions: incompressible, compressible, and solid. In other words, when this OpenFOAM layer is compiled, it will generate 3 .so files. If you want to know which file are included, you can look at this files incompressible, this folder. This file lists all the files that will be compiled for the incompressible libraries. Okay. At the same time, DAFoam also compile with reverse mode AD, because we need to use that for the air joints. When you compile this with reverse mode AD, you will generate 3 more libraries. In total, we will have 9 libraries when this OpenFOAM layer is compiled. They will be saved to this directory. Okay. So just keep in mind that to avoid any file IO, we rewrite all the OpenFOAM solvers into libraries. If you use OpenFOAM before, you know that when you run, for example, SimpleFOAM solver, this solver is a binary executive. We don't want to use that during optimization, because that will include a lot of file IO in the information transfer, which might not be very efficient. Everything happened in the memory during the optimization, which means that in the previous section, if you want to pass the mesh coordinate from the PyGeo component to the DAFoam component, this data transfer does not happen through file IO. Instead, it happens in the memory, so which is more efficient. This is the OpenFOAM layer overview. Let's look at the next, Sizen. As I mentioned, the main reason we use a Sizen layer is that this .so file from the OpenFOAM layer are pure C++ libraries. We need to wrap it such that it's callable from Python. And so which means that when this all run command, all make command is run, and both OpenFOAM and Sizen layer libraries will be compiled. And the Sizen library will generate dynamic library. The Sizen library like PyDASolver.sl or PyCurrentSolver.sl. And these libraries are callable from Python. Then we have the Python layer overview. So once this OpenFOAM layer and Sizen layer libraries are compiled, you just run this pip install dots. You will copy all these libraries to this side package DAFoam folder, such that it can be importable from the run script. So keep in mind that this run script of Py can only interact with the Python layer. It cannot directly access OpenFOAM or Sizen libraries. So the Python layer's main entry point is, as I mentioned, the DAFoam builders. Basically, when you initialize this class, you will allocate the memory, it will create a mesh, you will create all the flow variables. So how this works is that this DAFoam builder will actually call the initialize solver function for the PyDAFoam.py. I will talk about that later. So very similarly, other modules in the optimization framework, such as PyGL and Ideal, they use a very similar approach to wrap their computations into Python, such that we can call them in the Implicit framework. All right, that's overall how it works. Just one more comment is that all the actual computation are done in the OpenFOAM layer, which is written in C++, which is more efficient than the Python. That's why we do most of the computation in the OpenFOAM layer, but we do the data transfer in the Python layer. Now let's look into the OpenFOAM layer, more details. So the source code, as I mentioned, for the OpenFOAM layer are in this DAFoam src adjoints. Now I'm going to just go to that. Okay, so I download the DAFoam source code and put it here. So let's go to the DAFoam src adjoint. You can see that each folder here is a class. Okay, if this class has no child class, will look like this. You will see a .c and .n file. But if a class has child class, for example, let me go to DA Objective Farm. You can see that this DA Objective Farm, this is the parent class. It has many child class. If you want to add a new object function, basically what you need to do is just add the corresponding child class following the templates for other object functions. So you can follow the very similar logic if you want to add a new solve. That's the folder structure. Now let's look at the main entry point for the OpenFOAM layer. So which means that this is the main function, main class we need to look at when you need to add when you want to expose a new function in the OpenFOAM layer to the Python one. This is the main class. This is called DASolver, this class. Let me go to that. Let me clear this and go to DASolver class. Inside this folder, you can see that DASolver.c and DASolver.h, they define parent class. And then all the subfolder are a child class. For example, if you have simple form and you define it here. So let's look at in more details what's in this DASolver. H. So this is the main entry point, meaning that the Python layer can only call functions in this file. So if your function is in a different class, the Python layer won't be able to call it. So if you want to expose a function that is callable from the Python, you have to write the class, write the function right here in this DASolver.h. I'm going to move down. You can see that, for example, I'm going to search for. This is the function we compute the partial derivative of the objective function with respect to the state variables. You have to write it in this DASolver class. Okay, just give it an example. And so another very important thing is that this class has some general functions for the adjoints, but this class has some specific function for the solve flow, which means that if you want to implement the way to solve the flow, you can implement it in this parent class. Instead, you need to implement it in this child class, because each child class uses a very different way to solve the flow, but they use a general way to solve the adjoint, which means that all the adjoint functions are in the parent class, or the primal solver function are in the child class. Okay, so for example, if I go to this child class, the simple form, if you look at the file structure, it's very, very similar to the OpenFOAM's built-in give me 1 second. Yeah, the built-in function folder structure. So let me go to this file, DASolver simplephone.c. Okay, so which correspond to the next slide. And there are two main functions in this folder, in this file. One is called initialize solver. Okay, in this function, you need to initialize the mesh, initialize the flow variables, initialize the adjoint variables, initialize the adjoint class, and such and such. This is very solver specific because for different solver, you might initialize different flow variables. This is one of the main functions in this file. Another main function is called solve primer. Again, this is the function that you actually use to solve the primer. So the flow, for example, the input of this function is the xv vec. This is the volume coordinates. The output is the w vec, which is the state variables. Okay, if I go down, by the way, the initialize solver, this function will be called only once during the operations, but this solve primer may be called multiple times during the operation because we need to solve multiple flows. Okay, the flow variables, the mesh is created only once. If I scroll down, you can see that the main loop in this code is very, very similar to the original OpenFOAM's loop, just called solve the U equation, solve the P equation, solve the turbulence equation. Okay, we basically wrap this OpenFOAM's built-in executive solver into libraries. Right, so let me exit this, go to the next topic. Yeah, this is just the slides just are the information we show you in this file. I'm going to skip this. Now let's look at some functions for the adjoint. As I mentioned, all the adjoint functions are in this file. In this .c, and then you can search for example, calculate df, dw, ad. This function implement how to compute the partial derivative df, dw, and everything's here because again, the adjoint is universal for all the solvers. That's why we can put it in the parent class. If you're not very familiar with how this child class and parent class or how virtual function works, I suggest maybe you can go to find a YouTube videos, and we won't be able to cover that today. Okay, the adjoint class and DASolver. Now this is the main entry point, which means that later on you will see that if you want to add a new function, you add this function in this DASolver class. And this DASolver class, by the way, I forgot to mention that this DASolver class will use many other classes in the OpenFOAM layer. Okay. Now, as I mentioned, we need to compile OpenFOAM in 3 modes: the original mode, reverse AD mode, and forward AD mode. And the reason is that we used operator overloading AD tool called CodePad to differentiate OpenFOAM source code. Because the way this operator overloading works, we have to compile these 3 versions into 3 separate libraries. And then when we run DAFoam, we can load these libraries at the same time. Okay. And again, because one differentiates this operator overloading AD tool, OpenFOAM's calculation becomes by default 3 times-ish slower, which means that when we solve the flow, we use the original version of OpenFOAM, which is not AD. But when we solve the adjoints, we use the AD version of OpenFOAM. Okay. So when we compile this OpenFOAM layout, all the libraries that are for AD, reverse mode AD has the name called ADR. All the libraries that is for forward mode AD has the name like ADF. As an example, you know that OpenFOAM has a library called finite volume.so. This is for the original OpenFOAM. When we compile this with reverse mode AD code, it will generate a library called finite volume ADR.so. So finite volume ADF.so. At the same time, we can read in these 3 libraries at the same time. That's the main reason we want to separate these libraries. Now let's look at the size and layer details. So the size and layer, as I mentioned, it implements no new things. Instead, the only thing it does is that it just wraps the function in the DASolver into the library called PyDA solvers. Now let's go into this Sison layer. The source code in the Sison layer for the Sison layer is in this folder, PyDA solvers. And inside you can see some Sison file and C++ file. So now let's look at this DA solvers.h. What does this do? The way it works is that we're going to create a new class called DA solvers. Remember, this is different. This DA solver is for the Sison layer and DA solver is for the OpenFOAM layer. There is a reason for that. Yeah, I got questions about computational cost for the forward and reverse mode AD. Yes, the computer, if you just differentiate OpenFOAM using the operator overloading, for example, and you don't do any AD operation, just run the flow solver simulation again, this calculation becomes about 3 times slower. That's why we don't want to use the reverse AD mode to compute the flow, because that would be 3 times slower. For the forward mode AD, it's more or less the same, 3 times slow. That's assume that you don't do any AD. But if you want to add some ADC to compute the reverse mode AD, it will become even slower. In terms of memory, and we don't do we haven't done a very comprehensive evaluation, but it will be, I will assume that maybe you will use at least 2 or 3 times more memory than the original AD code, or original non-AD version of OpenFOAM. Hope that answers your questions. All right, let's continue. So keep in mind that this yeah, I got a following that question at 2 or 3 times more memory. That yes, because when you AD this use operator overloading, it will replace the data type for any scalar or vectors in this code. Before, a scalar only saved 1 number, but when it is AD, it needs to save at least 2 numbers, 1 for the value, 1 for the derivative. So by default, the memory cost will be 2 times higher. All right. If no more following our questions, I will continue. So the DA solvers are for the Sison layer, DA solver is for the OpenFOAM layer. The reason is that we want to separate the OpenFOAM layer, make it a pure C++ classes. We don't want to directly drop the class in the OpenFOAM layer. The reason is that OpenFOAM has its own mechanism for example, some runtime selection mechanism. We want to keep this mechanism unchanged. That's why we create a new class, which is called DA solvers. Essentially, on the right-hand side, I'm looking at a source code for this DA solvers. It does nothing but call the function in DA solver. This DA solver PTR is a pointer that points to the OpenFOAM layer class, and it will call the same function. So basically, this is a pure wrapper class, DA solvers. By doing this, we can create some completely independent C++ classes that use the exact same syntax, exact same logic and code structure in OpenFOAM. That's the main reason we want to create a separate Sison layer instead of directly wrap this DA solver from the OpenFOAM layer. Okay, so which means that that impacts the way you add a new function for DAFoam, which we will talk about that later. So this is the Sison layer. And another thing in the Sison layer, another important file in the Sison layer is this PyDA solvers.h. It also, you need to list the function you want to expose to the Python layer from the OpenFOAM layer. So you can see the list of functions here. And if I go to the bottom, a list of function implementation. This is a pure Sison files. So because of the time being, I probably won't be able to elaborate on details, but we will have some hands-on examples later. Just keep in mind that the Sison layer just wraps some functions from the DA solver class in the OpenFOAM layer. So here, just slides that just show you a few more details. Okay, a few notes. We cannot directly pass a Python array to the OpenFOAM layers. We have to pass them as passive vector or matrix. If you manage to figure out how to pass a Python array, for example, NumPy array, directly from the Python layer to the OpenFOAM layer, please let us know. For now, we don't have a good solution. That's why we pass them as a passive vector or paxi matrix. That works very well in parallel. So another thing is that when pass a character type from the OpenFOAM layer to the OpenFOAM layer, we need to use this encode in the Python layer. The third note is that the Python layer cannot call OpenFOAM layer member. It has no callback function. Okay. Oh, sorry. The Python layer can call OpenFOAM layer members, but the OpenFOAM layer cannot call any function from the Python layer. Any questions about the overall structure for the Python or OpenFOAM before we go to the Python layer? Okay, if not, let's finish this last topic and code structure, which is Python layer. So there are actually two main files in the Python layer. Let me show you where it is. They are in this folder, in the DAFoam folder. So the first main Python layer file is called PyDaFoam.py. It's very similar. If you use ADFlow has a very similar file called PyADFlow. This we in DAFoam we have a file called PyDaFoam, and this is the main interface that allow us to call the OpenFOAM layer functions from Python. In version 3, we add a new Python interface, which is called Dvs.Foam, which basically set up some predefined components for the optimization. Okay. For the time being, I'll just very quickly look at PyDaFoam, this class. And in the beginning, it has a class called DA options. If you have new options, you need to set out this new option here. For example, if you have new option from here, you need to set it and give a default value. So in this file, we also have a PyDaFoam class, which essentially initializes the solver and provides the interface to compute the partial derivatives, to compute the solve the algebra in such and such. For example, if you look at this line, here we initialize the solver. If you remember, this function is in the OpenFOAM layer. So when you call this function from the Python layer, the OpenFOAM layer will allocate the memory, create the mesh, create a flow field, and so on. So because of the time being, again, I won't be able to talk about details, but you can always refer to the instruction in the slides. Okay, now let's look at another main Python layer file, which is Dvs.Foam. Okay, in this file, we defined the DAFoam builders, which if you remember, we can call this in the run script.py. This is the main entry point for the Python layer. Okay, when you have this, you call, let me scroll down to the place where we initialize the solver, which is right here. So you can see that this DAFoam builder will initialize this PyDaFoam class, which is in the PyDaFoam file, and to allocate the memory. After that, it will do a lot of other things, like, for example, create a DAFoam group. And if you remember, you saw a group of components that includes IDWAP, DAFoam solver, and the aerodynamic post-process. And that group is created here. There are many other things this class is doing, and without looking at a specific example, it's very hard to explain for now, but later we will try to add some new functions into it, then we will explain how this works later. This is another files in the Python layer. Now that's it. That's a very, very brief overview for the code structures. Now let's look at how do we add a new feature to DAFoam. So we will start with the most general steps. Let me see. To do this, we need to first go to the workshop, and for that, we have an example here. In this example folder, we include a very light version of DAFoam that includes the only very minimum things you need to compile DAFoam that allow us to compile it very quickly and test our new feature. The thing you need to do is to just go to this folder. So by the way, let me go back. Of course, you need to start the Docker. Okay. Create a Docker container, and then go to the DAFoam lights, this folder, and call onMake. And you should be able to compile this. And of course, this is the default version. We don't have any new feature implemented yet, but after we implement a new feature, we need to compile it. So I can skip compilation. And after that, you do pip install this command to copy the Python libraries to your site package. After that, we also include a very simple example like CurveQ in this case. You can run this run script to test your new feature, for example, and it will run very quickly. So that's the overall process. How do you modify the code, compile it, and test it? Now let's look at a more specific example. The very first example is that, what if I want to add a new parameters to DAFoam? How do I do that? So let's go through the process. Follow these steps. So for example, if you want to add a new flow parameter called new parameters, these are the things you need to do. First, add this parameter to the DA options initialize function in py.dafoam.py. So I'm going to show you where the file is. So now in your container, go to the DAFoam light, and then go to the view DAFoam, py.dafoam. So okay, view this file, and let me set no wraps. Okay. So you can go to this class called DA option. Okay, this class has function called initialize, and then you can add your new parameters here to anywhere you want. But we separate some basic. But for the test purpose, I will just add it here. New parameters equals 0.0, and keep in mind that give a default value for these parameters. If it's an integer number, you just say 0. If it's a float number, it's 0.0. This is very important because DAFoam will use this default value to decide what type of this value it will be. If you assign a different value in the run script, you'll probably get an error. Okay, add this to this. Okay. Then what's next? We go to the next step, is that to, for example, use these new parameters in the OpenFOAM layer, because we did set it out in the Python layer, we haven't actually get a chance to use it, how to get it. So let's go to the, if you remember, OpenFOAM layer source code is at Adrian's src, and we go to the Dvs Solver class, because that's the only place you can implement your new features. Okay, if you want to expose it to the Python layer. So the way we do it is that we can go to this DA simple, this class, this child class, because we're going to use that in the run script. And then we have view this file, basically this file, DA simple form.c. Okay, once you are in this file, you can go to the any place you want. You can just get the new parameters and print it. That's what I'm going to do. So in order to do that, I go to the very bottom of the solve primer function, which means I want to print these parameters after the primer is solved. I just go to the very bottom of this. Right before I print end, I will say, okay, I'm going to get these parameters from the DA options pointer, get options, the name of these parameters, new parameters. This parameter will be passed to the OpenFOAM layer from the Python. Okay, and then I'm going to just print it. I can just basically copy paste this. This get this value from the DA option class, and then print it. And I print end. What I'm going to do next is save this file. Okay, and then I need to recompile DAFoam. So let me go back here. Go back one more layer and call this onMake function to recompile DAFoam. So you should compile and in about maybe 1 minute-ish, because I exclude all the file that are not necessary for this case. While it's compiling, I want to do another thing, which is that how do we know that this is implemented in the right way? So we add it in a py.foam file. We print it in the OpenFOAM layer. How do we know that it's actually implemented? After this compilation is done, I'm going to show you how to kind of validate if this feature is added. Well, if you can see me, I can show you another terminal. Yeah, right. This is another terminal. The other one is still. So I got another question that during this process, do we only recompile DAFoam, no other libraries like OpenFOAM? That's true. So when you have a new feature, you don't recompile OpenFOAM. We only recompile DAFoam. So give me one sec. Since that the compilation is almost done, we can just reshare this window. So if the compilation is done, you can see something like this. You also remember to run this pip installer dot. Okay. So we can double check if this library is compiled by going to this DAFoam library type ls. You can see that it's a new library called PyDASolver incompressible.so, and this is a sizing class. And then when we run this command pip install dot, we will copy this library to the side package folder such that it's importable from a run script. Now, what's next is that we have add a feature, recompile it, go to the curve queue, this folder. In the curve queue folder, there is a run script.py. We're going to go into this run script.py, and we're going to set a different value for this new parameters. For example, we can go down here. I can add it to here. Remember to add a comment at the end of this line. Okay, this is Python syntax. Okay, now we set a new parameters and set it to 12.3. Let's see if you run it, if you can see it from the Python from the OpenFOAM layer. Run it, you run the solver. You can see that at the end of the simulation, it print out the new parameters 12.3. So this basically verified that the new parameters we set in the run script get passed into the OpenFOAM layer. It get printed out at the end of the simulation. Okay, so any question for this new feature? Okay, very good. So now let's look at the next example. But today probably I will just go over 3 examples instead of all of them, because here are a few notes for adding the parameters. As I mentioned, that make sure you give a default value for the new parameters you have. If it's a dictionary, you can give it an empty dict, so that Python will know that it's a dictionary. So the parameters will be passed from the Python layer to OpenFOAM layer through the DA options object. This is done only once when this object is constructed. For example, in the future, say during the optimization, can I update these new parameters? Yes, it can be updated, but you need to call this function DASolver.update options. When you call this, this OpenFOAM layer will look for the new changes in all these DA options and then update it. If you don't call this, even though you update it and in the Python layer, you will not be updated in the OpenFOAM layer. That's why you probably see that in the angle of attack function, you always call this. So once you update the parameters in the Python layer, remember to call this to update the same thing in the OpenFOAM layer. Okay, I got a question set asking that this update DI options, does it apply only to the parameters or it applies to everything else, like other functions? The answer is right. This update DI options only apply to a new parameters. It does not apply to a new function, okay? All right, but the last note is that OpenFOAM layer won't be able to change the parameters from the Python, okay? That's everything you need to know for adding the new parameters to DAFoam. If no more questions, I'm gonna go to the next. topic, which is how to add a new OpenFOAM layer function and expose it to the Python layer. For example, I want to implement my own general function to compute the volume of the mesh. And then I want to call these functions in the OpenFOAM layer and print out the total volume, okay? And then I want to basically call this function from both the OpenFOAM layer and the Python. How do we do that? Let's go through this process. Okay, so the very first thing you need to do is to, of course, add this function into the OpenFOAM layer. Because again, we don't do any actual computation in the Python layer. Every actual computation, for example, computing the volume, needs to be done in the OpenFOAM layer. As I mentioned, the only entry points for the OpenFOAM layer is this DA solver class. Because this calculate volume is considered to be a very general operation, it shouldn't be solver specific. That's why we can add it in this class. Let's just go to that class, DA solver lights, and then src adjoins solver .h. Okay, we just view this function. What I'm going to do is that I'm going to just copy and paste this function. I assume that you are familiar with C++. This is a pure C++ function. I want to add it somewhere in a public members such that it can callable from outside. So you can basically add it anywhere. For example, I can add it here. Okay, well, the format is not very good. I'm going to change a little bit. Okay, let's very briefly look at this function. What this function does is that you will set out a variable called volume, and it will loop over all the cells in a mesh. So the mesh pointed volume, loop over all the cells, and then add the cell volume to these volume variables. After that, print the volume to the screen. That's it. That's a very simple example. Of course, you can do your much more complex operation. What you need to do is just add a function in this DA solver.h if this function is universal. But if it's not, it's solver specific, you have to add this function in, for example, DA solver simple form, something like that. Okay, now I have added this function. What's next? So if you add this function, this is a pure C++ function. It won't be callable or even importable from Python, which means that we have to add the size and layer file, which is right here. I go to the size and layer. If you remember, size and layer is in here, PyDA solvers, and there are two files you need to change. The very first file is DAsolvers.h. So I'm going to open this file, and what I need to do is to copy this line and paste it here. As you can see that this is just a pure wrapping function. In this DA solvers, I define the function that has the exact same name, calculate volume. And then in this calculate volume, I will call DA solvers calculate volume function. So you can see that I basically wrap this function in this DA solvers class. That's it. That's for one file in the size layer. There's another file we need to change in the size layer, which is called PyDAsolvers.pyx, this file. Okay. For every new function you want to expose to the Python layer, you have to change these two files. Let me show you how to change that. Pyx. So first we need to define the templates for this new function we just have, which will be a wild function calculate volume. Okay. This is a new function. This is the first place we need to add. In the second place, we need to scroll down to the very bottom of this file. We need to create a sizen function to call this. And for that, I can just copy this from here. Of course, you can follow the syntax for other functions. And this basically, again, wrap this using sizen. Okay. And that's it. So we have written a new function in OpenFOAM layer, we also add the wrapper functions in the sizing layer. Now we can compile it. Let's compile this. Just make this file. So then our next question, while this is compiling, our next question is that now we have a new function that calculates the volume. It has been exposed in the sizing libraries. Then how do we call it from the Python run script? Okay, the only thing you need to add is to add this DASolver.solver calculate volume. So I'm going to explain a little bit how this works by opening up another terminal. So now I'm opening another terminal and go to this file, curve cube. Okay, in this file, you probably see a run script and directly call it from run script because the new class has been imported from this PyDAFoam. What we can do is that after the simulation is done, I add a new line in this run script. This is my Python layer script. This is the line I'm gonna add. Okay. So this line basically says I already create an object called DASolver. This DASolver has a solver object. Solver object is the OpenFOAM layer object. Then I call this function. Okay. So once this is done, let's see if we can run it well. And I have to go back to the previous window. So you can see that. Now this is a compile. I got pip installed this. Okay. And then I will go to the curve kill case and I press and run this new script. And if you run the primer, after the primer is done, you can see that it print out the new parameters. This is a new feature we just add. At the same time, you'll print out the total mesh, the mesh total volume, which is 0.3, about 0.3. This is very small. So which kind of verify that if you look at this calculate volume function has been correctly implemented in the Python, in the OpenFOAM layer, and we managed to call it in the Python layer. And any questions for this example? Okay. So a few notes. So we can add new function to any classes in OpenFOAM layer, but eventually we need to write an access function in the DASolver class because that's the only entry points that the sizing function can call. And another thing is that I want to mention this. You notice that I call DASolver.solvers, and DASolver is a PyDAFoam class. It has an object called solver. This solver is the original OpenFOAM library. So we sometimes, if you want to call some AD functions, you might see that sometimes I call this solver AD. That is the OpenFOAM layer that is compiled by reverse mode or forward mode AD. So these are two different objects. You can call them and if needed. So because in this case, I implemented in the original version of OpenFOAM, it's not AD, nothing's AD. I don't want to AD anything. So which means that I can do this. But if your new function needs to do some reverse mode AD calculations, the way you call that is through this DASolver.solver AD, and then followed by the name of their function. All right. If no more questions, let's go to the next. This is the last feature I want to talk about. I think this is very common. What if I want to add a new objective function or constraint function? For example, I want to compute the stability margin, or I want to compute the average velocity in the flow field. It happens that this function is not in the DAFoam, and I want to add it. How do I do that? Let's go through the process. So the very first thing is I want to exit this file, go to the DAFoam lights, and go to the SRC, Adrian. Again, you want to add a new objective function, you want to add it in the OpenFOAM layer. you go to the DA objective form. So in this file, you can see that we have a parent class called DA objective form. We have one child class called DA objective form force. So very first thing you need to do is to make a copy of this force to DA objective form. Let me call it my object.s.c. Okay. Then we do the same thing. So use an existing function and rename it to the object function name you want to have. For example, my object form. Okay. Then what's next is that go into this new object function, just create, for example, .c, and then you can see that, well, these are the template from the object function force. I don't want to use this. I want to use my object. The next thing you need to do is replace all these keywords to this. So I can basically replace everything that is called DA objective from force to DA objective from my object. Okay. Another thing you need to replace is in the first two lines. And sometimes you are still call this, but now it seems to be fine. Okay, I replace all this for this file, and I do the same thing for the .h file. Okay, replace everything. Okay, now this class is called DA objective from my object. But it's one thing that's sometimes very easy to miss is that the type name in the .h file, this is the name you give to this new objective function. I don't want to call it force because it will conflict with an existing objective function's name. I will call it maybe my object, something like this. Okay, then when you set up this objective function in the run script .py, you need to use this name, my objective function. Okay, and that's it. If your objective function happens to be the force, then you can recompile, you should be able to use it. But in this case, imagine that our objective function is not force. We want to implement something different. How do we do that? Well, the very first thing is to remove some variable that is not needed. For example, this, I don't really need this stuff. This is for the force calculation. I can basically delete everything here, and that's it. I can delete this and a .h file, and I can also modify the .c file. Okay, so because this function is so simple, and I can basically delete everything here. Again, this is for the force calculation. I basically delete all of them. And you probably want to read the scalar. Can delete all of this. Yeah, if you want to delete all, then it's fine. So I just want to delete this and then delete a lot of things in here because I really don't need to calculate the force. And also this function, we can delete that. It's a bit long. Okay, here we go. So now we have a very empty objective function. Then what we need to do is just copy paste this. This is our actual implementation. Again, this essentially calculates the volume of the volume weighted pressure and the whole flow field. So, and this calculate objective function is the main function we need to implement. And the main output is objective function value. Okay, so which means that we will loop over all the, maybe it's better to look at here, we will loop over all the pressure cells and then compute the pressure times the mesh volume and sum them up. And then sometimes we might want to run it in parallel, which means that we have to reduce all these average pressures from all the processes to get a final value. And then we return. Okay, that's all the implementation you need. If you save it, you can go back and recompile. Hopefully we don't have an error. If you have an error, we need to look at what's going on. see. Let's wait for a while. So while it is compiling, and let's look at what else do we need to do, because we have add this object function in the OpenFOAM layer. Do we need to add any sizen or interface? The answer is no, because this is just new add. It is very much like add a new parameters. We don't need to. It's not a new function, so we don't need to change anything in the sizen layer. The very last thing we need to change is the key in this runscript.py, because if you remember in runscript.py, we need to specify what are our objective functions. Okay, we have a new objective function. If you don't use it, it won't show up in the optimization. So which means the very last thing is to copy this in the runscript.py. Yeah, I think this compilation will be done very soon. Right. Yep. Okay, when this is done, we call this p-dots. And we go back to the curve kill case and view the runscript.py. If you look at this, we have CD as our objective function. In this case, of course, we want to add another objective function called my objective function. So we can give it any name, like F1, and the type is the name we just set in the type name. In this case, if you remember, I set it to this, and you can delete all the rests. Okay, so then you can run it, see if that runs. Okay, so I made a mistake by forgetting. So if we see this error, it probably means that this new objective function is not compiled at all, because obviously I missed a step. And the previous here, I forgot to add this function to this file, files incompressible. So because that if your file is not in, if you create a new file and this file is not in this makefile lists, it will not be compiled at all. And let's recompile it. Oh, so now when you compile, sometimes you see an error says, okay, this is does not have any file called this, and this is probably means that we forgot to delete something. By the way, I have a template for this new object function in the DAFoam folder. Let me take a look at. Does not have any file called DA. Okay. Obviously, I delete the file, this class in the .h file, but I still want to initialize it. That's why I get an error. This should fix the error. Again, if you want to add a new object functions, I assume that you have to know how the OpenFOAM works. So because you need to add a new feature to the OpenFOAM layer. Looks like it compiles fine. And let's just. All right, so let's try this. Install dots. And we go back to curve cube. And then we can run it. You can see that now it runs. And during the simulation, you can see that not only the CD, but also our new objective function called F1 is printed out to the screen, which is the average pressure, which kind of verified that our implementation is correct. This is the overall how do we add a new objective function. Any questions? I think that's the last example we're going to talk about in today's workshop. If no more questions, and that's it for today. And thank you very much again for your interest in using DAFoam. And after this workshop, we will post the video recording and updated slides and to the YouTube and to the DAFoam website. Thank you very much.